Inside the air-insulated substation, we need to interconnect all of the equipments together in a safe and cost-efficient manner. To do this, we use conductors and busbars to carry the electrical energy between the equipments, and connectors and clamps to join the conductors and equipments together. By the end of this section, you will understand the different types of conductors and clamps that we use, and how these fit together into a fully functioning system. The aims of the course today are: introduce the different types of conductors and clamps that we use on air-insulated substations. See how we choose the type and size of the conductor. Look at the different types of clamps that we use. When we are selecting which busbar to use, we need to take the following parameters into account. The currents. This includes the continuous current rating and the short circuit current rating. The structural issues of the conductor. This takes into account the conductor dead weight, the ice covering on the conductor, the wind loading on the conductor, and the loadings that occur on the conductor during short circuit currents. Let's look first at the continuous current carrying capacity. As the current increases through a metal conductor, its temperature naturally increases. The higher the current, the faster the temperature increases. The temperature rise tends to be the limiting factor for most conductors. The generally accepted maximum continuous operating temperature for open busbars is taken at 70 degrees Celsius, which is 30 degrees Celsius over the 40 degrees Celsius ambient temperature. This limit is imposed to prevent heat flowing from busbars to the connected apparatus. We normally use the manufacturer's catalogues to select a suitable conductor that can carry the current level that we require continuously without exceeding the defined temperature rise. Next, we have the short circuit rating. Here's a typical table from the standards, which shows the short circuit rating for different nominal system voltage levels. As we can see, as the system voltage increases, the short circuit rating increases, and at 400 kV, it could be as high as 63,000 amps, which is obviously a huge amount of energy. The busbars need to be rated to carry the full short circuit rating for the time specified. This is usually 1 second or 3 seconds. Once we've decided on the substation short circuit rating required, we choose the conductor from the manufacturer's catalogues that meet this required level. Again, you will find that the limiting factor in this selection will be the temperature rise of the conductor. The dead weight of the conductor in kilograms per meter can be found from the manufacturer's catalogue. This can then be multiplied by the length of the conductor per span to determine the weight carried by each structural item. In cold climates, the weight of any ice on the busbar should be added to the dead weight of the conductor. The thickness of the ice depends on the worst case conditions. An ice weight of 912 kg cubed per meter is normally assumed. To calculate the effect of the wind on the conductors, the following formula can be used as a good approximation. For a typical open terminal substation with the busbars at 10 meters off the ground, P, the wind pressure in Newton meters squared, equals 0.613 times by V squared, where V is the wind speed measured in meters per second. Using this information, F, the force applied on the busbar in newtons, equals the wind pressure P from above, multiplied by A, multiplied by a constant CF. where A is the projected surface area. Cf is a constant that depends on the busbar shape. For a round busbar, Cf equals 0.7, and for a rectangular busbar, Cf equals 1. As you would expect, the force applied on a rectangular busbar will be higher than the force applied to a round busbar. The force exerted between parallel conductors from a regular short-circuit fault can be calculated as follows. Force between the two conductors F in newtons per meter equals 0.2 times by K, which is a constant, times by the short-circuit RMS current in kiloamps squared. This is divided by the spacing between the conductors in meters. For rigid conductors that can't move, the value of K depends on the type of fault. The value of K for two-phase faults equals 4, and for three-phase faults equals 3. For flexible conductors that can move slightly, the value of K depends on the span length between the conductor fixings. As the span length increases, the value of K reduces. So for a span length of 50 meters, K equals 1.06. What can we see from this calculation? Well, the main component is the square of the RMS current. So the current doesn't need to increase much for the force between the conductors to increase significantly. And, as you would expect, as the spacing between the conductors reduces, the force between them increases. Let's do a worked example. For a 400 kV system, having a three-phase short circuit with an RMS current of 41.9 kiloamps, calculate the force generated between two solid-type busbars spaced 3.6 meters apart. From our previous equation, the force exerted equals 0.2 times by K times by the short circuit current squared divided by the spacing between the busbars. Putting the numbers in now, this equals 0.2 times by K times by the short circuit current, which is 41.9 squared, divided by the space between the busbars, which is 3.6 meters. What's the value of K? Well, this is a rigid type conductor and it's a three-phase fault. So therefore, from the table, K equals 3. Putting this value of K into the equation now, the force exerted equals 292 Newton meters, which is obviously a significant amount of force. Therefore, when we design the clamps and connectors and the post insulators that carry the busbars, we need to take this force into account. In my experience, the main structural factor that we need to focus on is the dead weight of the conductors, together with any specified ice covering. We obviously have to go through the process of calculating the wind and short-circuit forces, just to prove that supporting structures, clamps, and conductors can resist such loads, but I have never had to change the equipment to deal with such factors. The physical strength of the busbars defines the span that we can use for the post insulators and other equipment that support them. Here we have a flexible conductor supported by two post insulators. The span is the distance between the post insulators. Flexible conductor will tend to sag as the current and conductor temperature increases. If the sag is too high, it may infringe the live conductor's safety clearances from the ground, and we need to take this sag into account when choosing the height of the post insulator structures. It is for this reason that we only use flexible conductor for short spans, and up to certain voltage and current ratings. Line conductors, stringers, and droppers use flexible stranded conductor. The cross-sectional area of the conductor defines its current carrying capacity. To get the required cross-sectional area, we can have a large amount of small conductor strands or smaller amounts of larger conductor strands. To simplify things, there are international standards that give the different conductor types unique names. These tend to be based around types of animals, birds, insects, or vegetables or fruit. An example is from British Standard 215 Part 1 for aluminium conductors. As we can see, this is based on insects. Each of the different conductors has a different diameter, number of strands, physical characteristics, and current rating. And from American ASTM B 231-B for aluminium conductors, as we can see, this is based on flowers. To achieve longer spans than flexible conductor, we can use solid, rectangular, or box conductor, which have a much higher rigidity and physical strength than stranded conductor. The two main materials used are copper and aluminium. The different shapes and sizes of conductor all have different current carrying and structural properties. The decisions on which to use depends on the system currents and span lengths required, and the relative costs of the conductor per meter and supporting structures. For higher voltages above 132 kV and high currents above 2000 amps, it can be more economical to use aluminium tubular busbar. Aluminium tubing has an excellent structural strength, which allows for significant spans to be used. This can reduce the quantity of post-insulators required. The round tubular shape makes full use of the electrical skid effect, where a high proportion of the currents flow down the outer dimensions of the conductor. The conductor costs and associated costs of clamps and connectors can be higher than conventional conductors, and this needs to be taken into account when selecting this type of busbar. Designers have a wide range of busbars and conductors available when they design an air-insulated substation. As usual, the main driver is cost, and the designers will choose the most cost-efficient option that meets the electrical and structural requirements. On substations below 132 kV, the minimal electrical clearances results in the space between the equipment not being particularly large. This gap can easily be bridged by stranded conductor. For substations above 132 kV, the clearance distances and space between the equipments increases, and rigid busbars are used. At the top end of the voltage range, the skin effect comes into play, and aluminium tubular busbar is favoured. Clamps are used inside substations to connect the conductors to the busbars and other equipment inside the substation. They carry the full system current and therefore need to be rated the same level of currents as the conductors and busbars that they interface with. As you would expect, they come in all shapes and sizes. The clamps need to be sized to carry the currents flowing through the circuits, be able to handle the weight of the conductors and busbars, and also the short circuit forces exerted under full fault conditions. They are normally made from aluminium or bronze and are connected to the equipment and the main conductor using torqued bolts to hold them firmly in place. We also need to provide expansion joints for the conductors, as they heat up and cool down when the currents increase or the ambient temperature changes. These expansion joints normally consist of flexible conductors or straps connected to the main body of the clamp, which allow the main conductor to move. where different material types are used for the two conductors being joined by the clamp, special bimetallic clamps are used. If we don't do this, the ionic transfer between the metals will deteriorate one of the metals over time. The best source of information for which clamps to use are the specialized manufacturers of these equipments. In my experience, on larger projects, if you give the clamp supplier a layout drawing of the substation and indicate the type of bus bars and equipment that you want to use, they are quite happy to give you a detailed schedule of all the clamps that you will need to implement. The clamp schedule is very repetitive, as most of the equipment bays that have the same equipment will all need the same type of clamps. So once we've designed one bay, this can be multiplied out to give the quantities required for the whole substation. As the substation voltage increases above 132 kV, we start getting issues with the air breaking down in certain sections of the bus bars and conductors, particularly at locations where we have right-angle bends and edges. These breakdowns are called coronas. To minimize the impact of these coronas on the system, we use corona rings, so that the breakdowns are contained and flashovers are reduced. Here's some typical corona rings. The corona ring is electrically connected to the high voltage conductor, encircling the points where a corona might form. Since the ring is at the same potential as the conductor, the presence of the ring reduces the potential gradient at the surface of the conductor and reduces it below the disruptive potential gradient, which limits the corona that might occur. Let's summarize what we've learned today. To connect the equipment together inside an air-insulated substation, we use line conductors, droppers, and bus bars. When selecting a bus bar, we need to consider its electrical and structural properties. Clamps are used to connect all of the conductors, bus bars, and equipment together inside the substation. Congratulations for completing this section. You should now have an appreciation of the different types of conductors and clamps that we use inside an air-insulated substation, and how they all fit together into a fully functioning system. I've attacked some questions on today's section to test your knowledge.